Hello friends, welcome to today's lecture, Influence Line Diagram. Myself, Mr. Y. S. Patil, Department of Civil Engineering, Sharad Institute of Technology, College of Engineering, Ketrao. In this lecture, we draw the ILD for a compound beam. Draw the ILD for support A, B, shear force and bending moment at G, shear force and bending moment at H. This is a continuous beam or compound beam supported at A, B, E and F, and in between C and D it is an internal hinge. Before starting the problem, we just discuss about what is meant by compound beam or how it is work. So basically ABC is a overhanging beam, means supported at A, supported at B, and the BC portion is a overhang. Then this is the separated diagram. This ABC, it is a simply supported overhang beam. At point C and D, it is internal hinge. Due to internal hinge, it is a separated beam. That CD beam is a simply supported. Treat as a simply supported beam like this. This is a CD, and due to this or the CD beam, due to this RC, whatever the RC reaction occurs when load on in between C to D, that reaction we need to cancel because this is internal hinge, and internal hinge the resultant force is 0. So we require to apply equal and opposite direction force, that is equal to RC and direction is opposite. So whatever the RC, suppose in this case RC going in upward direction, you should apply a load on that ABC or that C point in a downward direction, and the magnitude of that load is equal to RC. Similarly, at point D, whatever the reaction at RD, you need to apply reaction RD at point D in beam that EFD or DEF, equal to that RD value and opposite in direction. And this EF is a, once again it is a overhang beam that supported at E and supported at F, and that DE is a overhanging portion. Means suppose when load between A to C, you just get value for RA and RB, no other values. Means at C point there is no reaction because it is internal hinge. Whenever the internal hinge occurs, at that point there is no any type of resultant force or any type of force. Means this is the C point and D point is a zero effect 4 points. Whatever the reactions generated at C, you need to balance it. Means whenever the load lies between A to C, you got only values RA and RB. There is no value of RE and RF. Then when load crosses this C point, means load comes in between C to D. When load comes between C to D, due to this load you got somewhat value of RC and you got somewhat value of RD. Means if you got the RC value, you need to nullify that effect and you need to apply the RC opposite in direction on the beam AB. So you need to apply RC force or RC reaction on member AB. Whenever they apply load RC on this AB beam, due to this RC you got somewhat value RA and somewhat value RB. Means whenever the load comes in between C to D, you got RA and RB. Similar way, when your load lies between C to D, same time you got value of RD. And if you got RD value, you need to balance that RD value. Means you need to apply RD force at point D on the beam EF opposite in direction. And when you apply RD force in this point, you got somewhat value of RE and somewhat value of RF. Means whenever the load lies between C to D, you got RE value also and RF value also. Then next, load crosses the D point, means load comes at point D to F. Whenever the load comes at D to F, there is no reaction at RA and RB because there is no reaction in RD and RC. If RD and RC will be 0, automatically RA and RB will be 0. Means if RC is equal to 0, automatically RA and RB is equal to 0. Then you got only RE and RF. Once again I repeat, when the load lies between A to C, you got value RA and RB. When your load lies between C to D, you got value RC and RD. If the RC value is there, due to that RC force, you got once again RA and RB. If RC is equal to 0, RA and RB is equal to 0. Similar way, if RD having somewhat value, then you got RE and RF. If RD is equal to 0, automatically RE and RF will be 0 when the load lies between C to D. Then load crosses that D point, means load comes in between D, E, F, this beam. So you got only RE and RF value, because when load lies between D to F, there is no RC value. And there is no RC, if there is no RC value, then automatically RA and RB will be 0. This is the structure, or this is the mechanism of this compound beam. Let us see ILD for various points. First, ILD for support reaction A. In this type of the beam, we solve another method. Basically, we know when the support means load at A point, reaction at A is equal to 1. So apply unit displacement is equal to 1. Apply unit displacement 1 at point A. And whenever the load lies at point A, same time RB value, or that B coordinate ILD for B is 0. So we need to calculate coordinate at C. So deflection means this is one point at point A. When load at A, RA will be 1. When load at B, RA will be 0, means so load moves to the B. Similar way, if you know this triangle by using similar triangle properties, next coordinate we can calculate easily. So I want to find out this coordinate at C. So I know the triangle, similar triangle property. This is a triangle AB and 1, and this is a BC, and this is the X value. Suppose this is assume as a X. So height of the triangle is 1, length of the triangle is AB is a 12, and this is height is equal to consider X, and length of this BC is equal to 8. So simplifying this equation, you got X is equal to 2 by 3. Means when load comes at point C, RA value will be 2 by 3. Next, load moves to that point D. Load moves to that point D. Whenever the load comes at D, the RC value becomes 0. The RC value becomes 0. And due to RC is equal to 0, means there is no reaction in between A and B. Means RD is equal to 1, RC is equal to 0, and that RC force applied on this AB beam. So RA is equal to 0. So this is the RA is equal to 0. And when load crosses this D point, there is no reaction between RA and RB, because already discussed in previous slide, whenever the load crosses this D point, you got only ERE and RF. So this is the coordinate at point A 1, at point B 0, at point C this is 2 by 3, and at point D it will be 0, and that right side of the D there is no reactions, means whenever the load crosses that D point there is no ILD for A point. This is the ILD for support A. Then next, ILD for support B, means now I apply unit load at B, or unit displacement at point B. So this is the unit displacement 1. Now join this A to B. Similar way, this line extended up to point C. So I want to first calculate this C coordinate. How to calculate C coordinate? By using similar triangle properties. We know the RB, means that coordinate at B is 1 at a distance 12, means that is 1 by 12. And now this is the X, and distance for this A to C is 6, 6, 4, 4, means 6 plus 6 plus 4 plus 4, that is 20. So 1 divided by 12, X divided by 20. So simplifying this equation, you got X is equal to 5 by 3. Means what is the meaning of this 5 by 3? When load at point C, this is the load, assume. When load at point C, the reaction at B is equal to 5 by 3. Then next, suppose this load moves towards D point. Means suppose load comes at point D. This is the 1 kilonewton load. So when load come at point D, automatically RD is equal to 1 and RC is equal to 0. And when RC is equal to 0, there is no reaction between A and B. See carefully, means understand it concept. Whenever the RD comes is equal to 1, RC become 0 and RC is 0, automatically RA and RB become 0. That's why when the load come at D, RB will be 0. And whenever the load crosses that D point, RB value will be 0 and it will be a horizontal straight line. So draw the ILD diagram. At point A, 0. At point B, there is 1. At point C, there is 5 by 3. This is the answer. At point D, it becomes 0 and next 0. So this is the ILD for support B. Then next, ILD for shear force at G. So basically already learned in first lecture of the ILD. When basically this due to this G section, the beam only consider this only AB beam. The beam due to this G point, beam is split up into two sides, that AG part and BG part. First, consider load lies between A to G. First, consider load lies between A to G. Means on the left side of the section, there is two forces. First one is a RA and second one is a unit load. And on the right side, there is only one force, that is RB. So shear force at G, when you calculate shear force at G, when load lies between A to G, consider right side. So right side is RB and that RB value is X by L, and right side upward force consider minus. So your SF at G is equal to minus X by L when load lies between A to G. This is the most important concept. So X is equal to, I want to shear force at G. So X is equal to 6 and L is equal to, for span AB is 12, that is 6 by 12 is equal to minus 1 by 2. Then next, load crosses point G. Load crosses point G. So now load comes at point B to G. Now on the right side, number of forces 2, that is RB and unit load, and on the left side there is only one force. So consider now left side, and we know that the sign conventions, left side upward force is a positive. So shear force at G is equal to RA, and RA becomes 1 minus X by L. 1 minus X value is a 6 divided by 12. So simplify this equation, you got plus 1 by 2. This is the minus 1 by 2 and this is the plus 1 by 2. So draw this sketch. Due to this, when load between A to G, this is a minus 1 by 2. When load lies between B to G, this is a plus 1 by 2. Next, extend, I want to calculate this C point, coordinate at C. So use similar triangle properties once again. The height of the triangle is 1 by 2, means that is 0.5, and the span of the triangle is, or base of the triangle is 6, that is 0.5 divided by 6. This is called as, this is considered as a X. This is the height X and the span is 8. So simplify this equation, you got X is equal to 2 by 3. This is the coordinate X is equal to 2 by 3. Then next, when load moves at point D, RC value 0, and if the RC value 0, automatically RB and RA value 0. And we know that the shear force at G, when load between A to G, is nothing but it is a RB, and when load lies between G to B, it is nothing but RA. So automatically RC is equal to 0. If RC is equal to 0, automatically this point reaction will be, both reaction will be 0. So there is a no shear force when load lies on the D point, and whenever it crosses that D point, there is no reaction at point G. So join all these points by straight line. This is the ILD for SF at G. Then next, ILD for bending moment at G. Once again, mark a section and just only consider beam AB. Mark a section at point G, that due to section beam split into two parts, right side of the G and left side of the G. First consider load lies between A to G, and on the left side there are two forces, that unit load and reaction, and on the right side there is only RB. So moment about G when load lies between A to G, reaction RB into 6. RB into 6. So X is equal to, bending moment at G is equal to X divided by L, that is RB, in bracket L minus X. Suppose this is the X, this value is the X value. So the distance is when load lies between A to G, maximum. I want to suppose load lies on G point. So X by L in bracket 1 minus X. Sorry, 1 L minus X. So 6 by 12, that X is equal to 6. I want to bending moment at G. So put up X is equal to 6 divided by 12. In bracket span of the beam is 12 minus X is equal to 6. So simplify this equation, we got 3. Then next I want to cross check when the load lies between, now B to G, now B to G. So bending moment at G is equal to, consider RA now, RA into X. Suppose I want to bending moment at G, so this is the X. So RA into X, and RA value is equal to 1 minus X by L, and into distance, this is the moment. So this is the X. And now X is equal to, put 6. So 1 minus 6 by 12 into 6, that is 3. Means when load considered between A to G, the answer will be 3. When load lies between B to G, bending moment at G is equal to 3. So both conditions, our value will be same, that is 3. This is for AB portion. When load lies between at point C, so I want to just draw a line from point G to B. When load lies at point B, there is a no moment at G. Then at point C, I want to find out coordinate at point C. So by using similar triangle properties, we know the height of the triangle is 3 when the base is, that GB length is 6, that is 3 by 6 is equal to, consider this is the X vertical distance and horizontal is a 8. So X by 8. Simplify this equation, we got X is equal to 4. This is the coordinate 4. Then when load lies at point D, once again, if load acting at point D, RC will be 0, and when the RC is equal to 0, you got RA and RB is equal to 0, means automatically all points will be 0. So draw the ILD and join all points. That first is a plus 3, means that A at point G is equal to, bending moment at G is equal to 3. Then bending when load lies at point C, the bending moment at G is a 4. So join this 3 and 4. This is the line directly join. This is the ILD for, and when load crosses that DEF, means there is a no reaction between RC, and if there is no reaction RC, means automatically RA and RB will be 0. Then next, ILD for SF at H. So this is the H point. First of all, when load lies between A to H, when load lies between A to H, number of forces on the left side is 3. This is RB, unit load, and RA. So now I consider right side of this section. Now I consider right side of the section. So number of forces right side of the H is 0. So our ILD is 0. Means when load lies between A to H, there is no reaction or there is no shear force at point H. This is the first concept. The next, when load crosses in between H to C, or that crosses point H and lies between H to C. So number of forces on the right side is only one, that is 1 kilonewton unit load, and number of forces on the left side is 2, that is RA and RB. So consider minimum number force side. So we consider right side of the H. So right side of the H is 4, number of forces is 1, and that is vertically downward. And right side sign convention, vertically downward force is considered positive. So number of force is 1. So when the load lies between H to C, when load lies between H to C, the ILD for or that shear force value will be 1. Means load lies between H, SF value at H is equal to 1. When load lies at C, SF value at H is equal to 1. Then next, this is the H, sorry. For beam CD, when load crosses that C point, means load comes now in between C to D. So at C point, when load lies between C, RC become 1, and RC acting on the downward direction on this beam AB. So RC become 1 and load become 1. So when load lies on C point, it become quantity is unit 1. Then this load moves at point D. This load moves at point D. So now RD become 1 and RC become 0. So when load beam CD, when unit load lies between C to D, a shear force at H is vary from 1 to 0. Means when load lies at point C, is SF at H is equal to 1 and continuously moves towards D, the value goes decreasing, and when at point D, value becomes 0. So this is the shear force at H. When load lies between H to C, it becomes 1 and 1, and when load lies between C to D, it becomes vary 1 to 0. So this is the ILD for H, shear force at H. Then next, ILD for bending moment at H. Once again, when load lies between A to H, when load lies between A to H, number of forces on the left side is 1 RA, second unit load, and third RB, and number of forces on the right side of the H 0. So we consider right side. Means when load lies between A to H, there is no moment, bending moment at point H. Then next, when load lies acting on exact H, when load lies acting exact H, bending moment at H 0, because the line of action and the point is same. Then next, when load lies at point C, when load lies at point C, so bending moment at H is equal to this load into perpendicular distance, and direction of the moment is clockwise. Right side clockwise moment consider negative. So bending moment at H, bending moment at H, consider this is H, by mistake let print G. Bending moment at H is equal to when load at C, that is load 1, distance 4, and direction of the moment is clockwise. Right side clockwise moment consider as a minus. So your bending moment at H is equal to minus 4. Then similarly, when load crosses or load moves C to D, when load acted at point D, your RC become 0. Once again, as per previous discussion, your RC become 0, and when the RC is 0, automatically H value becomes 0. So this is the when load at point D, your bending moment at H become 0, and when load crosses that D point, there is no reaction RC, so it will be automatically 0. So draw this ILD diagram by using this coordinate. When load lies between A to H, there is no bending moment at H. When load lies at point C, there is a -4. And when load lies at point D, there is a 0. And when crosses the low point D, it becomes once again 0. And that minus sign means minus sign indicates your negative bending moment. So you plot your coordinate should draw below bottom line. This is a alternate method to solve or to draw the ILD. Otherwise, you can solve this problem by using our conventional method or by using our considering previous lecture. So this is the ILD for compound beam. Thank you.